curve sketching. Take out a highlighter, highlight the word beautiful. A beautiful application is that we can more accurately sketch graphs using calculus than we were able to before. All those years of graphing in pre-calculus, and then we get to graph some more. So you learned techniques in previous years. How would you find the vertex of y equals 3x squared plus 12x minus 1? Yes, the sommet or whatever. Yes. So there's a good translation word from French to English. Because, yeah, vertex is like, whoo, no idea, right? So now, that's what vertex means in English. How would you find that from previous years? Change it into like this form? Yeah? Did you learn it with P and Q? Sometimes some textbooks use H and K, some P and Q. Okay. So how do you change it to that? You remember? Quick memory jog. You would factor the 3 out of the x squared and the 12x. You would leave the minus 1. You left a blank here because you wanted it in this form. So now we've got the 3 out in front. That's going to be a, but we want this to be something squared. Well, what would this have to be above so that we got x plus 2 squared? What would have to have been in here? Plus 4, right? And you might remember, oh yeah, we divide by 2 and then square to get that value. Maybe that was a thing you memorized, but maybe it makes sense if you're factoring that a perfect square, this will always be double what that number is. And this number that you're adding in the green space is always square what that last number is. Now, if I added 4 here, I have to do something in this other space to compensate. Because you can't just add 4 to a side. But if you add 4 and subtract 4 at the same time, that would cancel out. So what would I have to put in this space to cancel out that plus 4? A minus 12, right? Because 4 and minus 12 are exactly the same. Well, no, they're not exactly the same. But why is it minus 12? Because that 4 gets hit by that 3. So we've actually added 12. So to compensate, we'd have to subtract 12. And then this becomes minus 13. So our vertex is negative 2, negative 13. And that's how we found our vertex in previous years. Now this is a parabola. You agree that this parabola opens up? We now know that at negative 2, negative 13, and opening up, that our parabola looks something like this. Now something special happens at the vertex as far as thinking about calculus. When we take the derivative, what do we find? We find a tangent. And if we find a tangent at the vertex, what's the slope of that tangent going to be? 0. So any maximum or any minimum is going to have a slope of 0. How much quicker is it using calculus to find our vertex? Well, how hard is it to find the derivative? The derivative is going to be 6x plus 12. If we're looking for when is that slope of that derivative equal to 0, it happens at x equals negative 2, and we've already found this. To find out the y-coordinate, we can just plug negative 2 back into our original equation, and then you'll get negative 2, negative 13, maybe a little bit faster than completing the square. But the nice thing about calculus is this doesn't only find vertices of parabolas, but now any cubic function that has a max and a min, you can find those ones, or any function for that matter. If you can take the derivative and set it equal to 0, we'll be able to find those maxes and those mins. So our calculus that we learned in the last chapter is all about slopes of tangents, and those slopes can tell us a lot about the graph. Not only the maxes and mins that we talked about right before, but whether a graph is increasing or decreasing. So what does that mean? F prime of x is equal to 0. That means the slope of the tangent equals 0. And in the example that we just saw, that means that we had a maximum or a minimum. We're also going to see that this also can happen in other points where the slope can be 0. For example, in an x cubed graph, this point right there happens to have a tangent whose slope is 0. If the derivative is greater than 0, in other words, that means the slope is positive. What does that mean about our original graph? Let's think about a parabola. We already know that here the slope is 0. Where could I draw a point on that parabola where the slope is positive? Anywhere to the right. So I'll do that anywhere to the right, it's positive. What does that mean for our function? It's wherever our function, our original function, is increasing. Notice that our parabola is going up. After it's equal to 0, everywhere to the right of that, our parabola is increasing. And everywhere to the right of that blue line, our tangents will always be positive. And what does it mean if our tangents are negative? Well, can you see that any point I put along here will have a slope that's negative? And what does that mean? That means our original function is decreasing. So our slopes can tell us where we have a maximum or a minimum. It will also tell us where our original function is increasing and decreasing. So that too will help us draw our sketches of graphs more accurately. So here, we've done it already, so we're not going to do it again, but we could use calculus to find the vertex of this. Just to review, because we did it over here. We found the derivative, we set the derivative equal to 0, and then we found the x-coordinate that gave us a slope of 0. Once you find that x-coordinate of where the vertex would be, you could plug that back into your original equation to find the vertex at -2, 13. So we've talked about knowing that a function can be increasing or decreasing based on the slopes of the tangents. We talk about something being increasing if you go from left to right and you're going up, or if it's rising, then we say that the function is increasing. And similarly, if you're going from left to right and your graph is going down, we call that decreasing. So we're going to color code this. We are going to, in blue, label wherever the slope is equal to 0. All of our maximum and minimum points will be where the slope is equal to 0. we will label in green, or whatever color you would like, the sections that are increasing. That means as you're going from left to right, the graph should be going up. This part here is increasing. It's also increasing after there. And we're going to label in red wherever your graph is decreasing. Ooh. That'll be that section in there. And if you think about it, if you pick any point in any of the green sections, so if I pick that point and draw a tangent, that tangent has a positive slope. And if I pick any point in the red section and draw a tangent, that tangent will have a negative slope. It's a pretty bad tangent, but you get the idea. So this is saying the same thing again. A tangent line where it's increasing will have a positive slope. A tangent line where it's decreasing will have a negative slope. Those maximum and those minimum points that we labeled are called stationary points. And a stationary point is any point where that derivative is 0, or if you drew a tangent, it would be a horizontal line with a slope of 0. And for graphing, any time that our first derivative is equal to 0, or any non-permissible values for either our original function, and I added, I think I've got it in your notes, right? Any non-permissible values either for your original function or for your derivative, those are called critical numbers or critical points. And they're going to be important for us to find out what happens at those points, because those are going to be points where your graph is going to change, sometimes change from increasing to decreasing, sometimes not. But it's going to tell us about the shape of our graph. So we are going to find out where the following graphs are increasing and decreasing. We're going to learn sort of the formatting way that we can show this for each of these graphs and then make a sketch. Some of these graphs are going to be things that you know how to graph from before. Okay? And just as far as making a connection, do you remember solving quadratic inequalities? Like this one, y equals x squared minus 10x plus 21. You would have found out where it was equal to 0. So just off to the side here, just as a little reminder, if you were solving this, x squared minus 10x plus 21, you might have first found out where was it equal to 0 by factoring minus 7 minus 3, set it equal to 0, and found out it's equal to 0 at 3 and at 7. And then maybe you would have checked what happens in each of these sections. Do you remember doing true and false? Maybe? You plug in something less than 3. Plug in 0. What do I get? When I plug in 0, I get 21. Is that where the y values are bigger than 0? Is that where it's greater than this function? Yes. So you would have put in things like true, false, true, and made a diagram like that. We are going to do something similar now for curve sketching. And this is what it's going to look like. So here we've got a function. We know it's a parabola. We know it's going up. we know a lot of things about this parabola already because we've sketched parabolas before. Now, using calculus, we could find the derivative for x plus 1. And setting that equal to 0, we could find out our critical point. Now, critical points, again, are anywhere that your first derivative is equal to 0. They also include non-permissible values of your derivative and of your original function. But this function and its derivative doesn't have any non-permissible values. So our only critical point is -1/4. So where this is connected to that idea before is you're going to make a number line and put all of your critical points on there. So our only critical point is -1/4. So we only have one critical point. As far as what we're going to do with this now is we are now going to check values less than -1/4 and check values bigger than -1/4. Because at -1/4, we know that our slope is 0. In other words, this -1/4 is going to be the minimum of our parabola, because we know that parabolas have a vertex, and this one's opening up, so we already know that this one has a minimum value. If we plug in something less than -1/4, like -2, if I plug -2 into my derivative, it's going to tell me something about the tangents. Plugging that in, -2, gives me a negative slope. What does that tell me about my tangents? It tells me that all my tangents, if it's negative in this section, all of my tangents are like this, and that means my original function has to be decreasing. Similarly, if I try plugging in a value larger than -1/4, like 0, into my derivative, I'm going to get a +1. In fact, anything that you choose larger than -1/4 will give you a positive value. That tells me that all of my tangents in this section are positive, and my function has to be increasing. Now, this is a parabola, and we knew this already. If we drew this parabola, and we plugged in -1/4, so 2 times -1/4 squared minus 1/4 minus 21, we get a vertex at -1/4, comma, -21.125. And our parabola, we know is going up. We know that before from previous stuff that we've studied. But according to calculus now, it's telling us that since the derivatives are negative before -1/4, that our function has to be decreasing and then increasing afterwards, which is exactly what we know about our parabola opening up already. But this is the technique that we're going to use with calculus to do functions that we didn't know before. Here's another parabola. Again, similar idea. We will always take the derivative, set it equal to 0 to find our critical point. Check for non-permissible values in our original function and in our derivative. This one has no non-permissible values, so our only critical point is 1. We want to find out where our original function is increasing and decreasing, so we're going to check the slopes. So we're going to plug in values into our derivative less than 1 and larger than 1. So if I plug in 0, and you can pick any value less than 1. 0 is a nice one to choose because it makes the mental math easier. plug in 0, my derivative is going to be negative. If my derivative is negative, all my slopes look like that. That means my function, my original function, is decreasing before 1. And if I plug in a value larger than 1, say 55 million, then that'll be positive, and it will be increasing after. If I plug in 0 into my original function, it's positive 3. But what we're looking at is what's happening to our derivative. And that's why I put the green square around the derivative. We're always plugging things into our derivative. Plugging it into our original equation gives us a point on the graph. So plugging 0 into our original equation tells us that the point 0, 3 is on our graph. But it doesn't tell us about increasing and decreasing. Plugging values into our derivative is going to tell us things about increasing and decreasing. So for this one, as far as sketching our graph, what do we know? We know that our vertex is going to be at 1, and if I plug in 1 for x, I get 7 minus 14 plus 3. 1, negative 4. We already figured out our y-intercept because if we plugged 0 into our original equation, that tells us a point on our graph. We know we have the point, 0, 3 is a little bit higher than that, isn't it? There we go. Perfect. You can do that on your notes as well. And our function is decreasing until it gets to our vertex and increasing afterwards, which we already knew because of things we know about parabolas. So far, so good. We've only chosen things that we have graphed before, and we're seeing our results just like the things we've graphed before. Now we're going to do one that we've graphed before, but you've forgotten, right? Because I'm pretty sure parabolas are ingrained in your head. You know what they look like. You did 1 over x squared graphs in grade 11. They looked like either a speed bump. Sometimes we call them like little speed bumps, or they had a bunch of different shapes. So I'm pretty sure you might not remember exactly what a 1 over x squared graph looks like. And it's probably not something that immediately came to your head, just like a parabola probably immediately comes to you know what a parabola looks like. But a 1 over x squared, not so much. Okay? Well, we can write 1 over x squared as x to the negative 2. So finding the derivative bring the 2 in front, subtract 1 from the exponent. So we could write our derivative as negative 2 over x cubed. As far as our critical points are, we need to find out where our derivative is equal to 0. Can you tell that this never equals 0? How can I tell that? Well, for a fraction to equal 0, the only way a fraction can equal 0 is if the numerator equals 0. And our numerator is negative 2. Last I checked, that's never, ever equal to 0. So this fraction's never equal to 0. So does that mean that on our number line, we don't have to put any values if we're going to use calculus? We just have one thing? Well, but the derivative itself never is 0, so there's no critical points for zeros. But what else did we have to check for critical points? Non-permissible values. Does our original function have any non-permissible values? Yes. Our non-permissible value for our original function, x can't equal 0. Did our derivative have any non-permissible values? Yes. Happens to be the same one. X can't equal 0 there either. So our only critical point for this one is 0. Now, if we plug in values before 0 and after 0, what do we get? Again, where are we going to plug in values? We're going to plug in values into our derivative to find out whether our function is increasing or decreasing. If you plug in a -1, will our derivative be positive or negative? It'll be positive. So that means our function is increasing before. And if you plug in something larger than 0, you're going to get a negative. So we know that it's increasing before 0, decreasing afterwards. And when we go to graph this, we have to use some of our knowledge from before. One of the knowledge things that we're going to have to use from before is a knowledge of asymptotes. Hello. So what is our knowledge about what happens with the non-permissible value as far as asymptotes go? We're going to have an asymptote at x equals 0. What about horizontal asymptotes? Does this one have a horizontal asymptote? And if so, where is it at? Y can't equal 0 is a non-permissible value for y, so we will have an asymptote at y equals 0. Horizontal asymptotes tell us something about the function when it gets really, really big. You learned techniques for it before. Now that you've done calculus, basically what your horizontal asymptote is looking at is what happens as x gets really, really big to positive numbers. What's this limit equal to? 0. That's why we have an asymptote at 0. You could do the same limit at negative infinity and get 0 as well. So our asymptotes are going to be important because we know at our extremes it's going to be close to 0. So now how does calculus tell us what the rest of this graph looks like? Well, if I start at negative infinity and I have to be close to 0 and I have to be increasing, will I start above or below that horizontal asymptote? I have to start above if I'm going to be increasing. And then after x equals 0, will I start here at the top or here at the bottom if I need to be decreasing and approach this asymptote? And so calculus tells us that this is the only shape that makes sense at this point. Do you remember that graph now? And now for a graph that you've never done, a 1 over x cubed graph. Or have we done that? Did you do one of those last year in grade 12? So now this is the same as x to the negative 3. And if we take the derivative of that, we would get negative 3, subtract 1 from the exponent, or negative 3 over x to the 4. Is this ever equal to 0? No. So once again, this is never 0 because in order for that to equal 0, we would have to have the numerator equal to 0. So it's never equal to 0. Are there any non-permissible values? In our original function, x can't equal 0. Similarly here, in our derivative, x can't equal 0. So the only point that we're going to put on our number line, again, is 0. That's our only critical value. Then to find out whether things are increasing or decreasing, we plug that always into our derivative because we're thinking about slopes of tangents. And if I plug in something less than 0, like a -5, can you see that the bottom of my fraction here is going to be positive? Because anything to the power of 4 is going to be positive, but we have a -3 on top. So this section is going to be negative. That means our original function is decreasing. And after 0, if I plug in a value, the bottom is still going to be positive, the top is still going to be negative. This is going to be negative again and decreasing again. So when we go to graph this, and we use our knowledge of non-permissible values to add our asymptote at x equals 0, and we use our knowledge of limits, what happens when x gets really, really big on our original function? Y gets closer and closer to 0, so we will have a horizontal asymptote at y equals 0. Thinking about that and those asymptotes, if it's going to be decreasing to start with, what's the only possibility? If it's going to be decreasing after that. And here we have a general sketch of what 1 over x cubed looks like. So now this one was kind of new, but you did have techniques for doing this from grade 12. Do you remember? Here's just a quick review from grade 12. You remember that x cubed looked like this? So you learned techniques for graphing 1 over graphs that you already knew. What are some of the techniques that you learned? You learned wherever there was an x-intercept, you had an asymptote. If your graph went up or down forever, you had an asymptote there. What happens to a point like 2, 8? It became 2, 1 over 8. All of your, in reciprocal graphs, all of your y values became 1 over that y value. And so if you had done that, you would have got this graph as well. But maybe you didn't remember that technique either. Does that kind of ring a bell? Remember those reciprocal graphs? So if you can have any function to begin with, you can graph 1 over that function, and you learned some techniques to do that. Okay? The nice thing that calculus is bringing to us is it's bringing to us a technique